Hi everyone, today I just want to give you a quick intro to static equilibrium. So this is when forces are all balanced. In the previous section of forces we were looking at objects that were moving so we could figure out the acceleration. They could be stationary, but we are looking at what would be happening if they had an acceleration. This section, everything is stationary. So that would be the difference between, this would be the focus of civil engineering and any other type of force analysis. You have the two scenarios. Objects are moving, objects are not moving. So this is when they're not moving. So the key points in this, because they're not moving, the net force in the x direction equals 0. So all the forces to the right equal all the forces to the left. And the net force in the y direction is also balanced. So all the forces up equal all the forces down, which one of these scenarios was always true when we were working in objects that were moving. So if we were talking about objects are moving left and right, then we assume that the y direction they were balanced, right? And if they were moving up and down, then we assume they're balanced in the left and right direction. And then, of course, there's the inclined planes, but we did that with, we were assuming that they were on a ramp, and so they moved up and down the ramp, but they didn't move off the ramp or into the ramp. So, like all of them, we always draw our free body diagram, and we break it into our forces, into our x and y components. So this would be what an example might look like. Right, so we use cables, an extension of this when we switch to bridges and stuff like that. We're not going to have time for that, but if you at college or university, you might see the bridge scenarios, which is based upon what we're doing right now, and the torque that we will talk about after this. So how does it work? Well, if I do this, and I set it up, so I'm going to take each of these two components. I'm going to break them into x and y. I got a bunch of stuff on here, so don't worry about that at the moment. I'm going to break it into x and y. And if I do f net in the x direction, so I'll label these quickly. This is fx2, this is fy2, this is fy1, and this is fx1. So fx2 is to the right, fx1 is to the left. Since they're equal, then we know fx1 has to equal fx2. In every one of these questions, these two are equal to each other. If they're not, it's going to move until they do equal each other. The other scenario is that all the forces up, fy1 and fy2, minus the weight, are equal to the net force in the y direction. So f net is up minus down, so fy1 plus fy2 equals minus w. And we know it's also not moving in the y direction, so fy1 plus fy2 equals the weight. And that is true in all these scenarios. fy1 and fy2 are sometimes equal. So if these two angles are equal, from what you learned in math class, if these two angles are equal and these two sides are equal, then these two other sides have to be equal. So if we have equal angles here, if theta 1 and theta 2 are equal, then fy1 and fy2 will be equal. If these two angles are not equal, then these two sides do not equal each other. But the fx1 and the fx2 still have to equal each other. If one's bigger, then the whole sign will move one way or the other. A couple other things we'll need when we do these. We need to know Pythagoras. So the f1, so the hypotenuse is equal to fx squared plus fy squared. We're still using tan, and we're also going to need to use sine and cosine. And so just a quick review. Draw a free body diagram, label all the forces, break all the forces in the x and y components, solve for the unknowns using those set of equations up above, and we may need substitutions used for fy, which we'll show you when I go through one of these examples. I hope that makes sense. Thanks.